Hello everyone, and in this video, we're going to be taking a look at where the center of this red circle is. Specifically, we want to find out where the circumcenter of triangle BIC is, where I is the incenter of triangle ABC. And for those who do not already know about this lemma, you'll be surprised about where it is. It ends up being on the circumcircle of triangle ABC. This is a very strange fact, so obviously we want to prove this. Well, let's go ahead and draw the lines IO and BO. So if O is a midpoint of arc BC, minor arc BC, then we want to show that BO equals OI, as that would mean that we're done, because BO equals OC by circle properties, because O is on the perpendicular bisector of BC. So we want to prove this fact here. Let's try getting everything into angles. Well, the best way we know to get lengths into angles is isosceles triangles. So we want to show that triangle BIO is isosceles. Well, what would this mean about angles? Well, suppose that this angle here was theta, and that would mean that each of these angles here were 90 minus theta over 2 and 90 minus theta over 2. And that's what we want to prove. So if angle BOI is equal to theta, all this stuff can go, then we want to prove that angle BIO is equal to angle IBO is equal to 90 minus theta over 2. Well, how did we go about proving this? We want to somehow utilize the circumcircle of ABC because, well, O is on the circumcircle. So if we want to deal with BOI, B is already on the circle, but I is not. So we can extend OI to meet the circle at A. Why would it be at A? We know that BO is equal to OC, but by circle properties, angle BAO and angle CAO inscribe the same measure arc. So these angles here are equal. However, we know that angle BAI is equal to angle CAI. So that means that O must lie on AI. So anyway, we have that this is angle BOA. So now we have everything on the circle. So might as well continue using the circle. We can end up using a different angle to inscribe the arcing, angle BCA. This is really wonderful, as we now have everything in terms of the sides of the triangle. So this is 90 minus angle BCA over 2. And we want to show that this is either equal to angle BIO or angle IBO. If we were to focus on IBO, then if we were to get this on the circle, we'd have to extend it all the way here, and that's not in terms of the triangle that we have. It might make things a bit messy. So let's go ahead and focus on angle BIO. So our goal is to prove that angle BIO is equal to 90 degrees minus theta over 2, where theta is equal to angle C, angle ACB. Well, let's go ahead and get everything in terms of the triangle more. We know that A, I, and O are collinear, as we already said. So that means that since angle BIO and angle BIA are supplementary, that means that angle BIA, we want to prove that this is equal to 90 degrees plus angle BCA over 2. Now, some of you may already know that this statement here is true, but I'll go ahead and prove it anyway for those who don't. So we have that this angle here, angle BAI, is equal to angle A over 2, and similarly angle B over 2. And now we can use the sum of the angles of a triangle to get that angle A over 2 plus angle B over 2 plus angle AIB is equal to 180 degrees. And we want to prove that this is equal to 90 degrees plus angle BCA over 2. So let's plug it in and see what happens. We get 90 degrees plus, and then expressing all the fractions with the common denominator. We get A plus B plus C over 2. And we want to show that this is 180 degrees. Now, it's pretty obvious to see that angle A plus angle B plus angle C is equal to 180 degrees because we have a triangle. So that means that 90 degrees plus 180 degrees over 2 is equal to 180 degrees, which is obviously true. So we have actually shown that the center of the circle circumscribing a triangle BIC lies on the circumcircle of ABC. We can actually go one step further with this by constructing a diameter of the circle. Sorry if this is not a really good diameter. Let me draw a better one. There we go. And this angle here is 90 degrees and 90 degrees. And then this intersects at a point I suppose A, because it's opposite the side A here. Well, we can think of this point IA in another way. If we extend the side here, then given any angle here, the angle bisector of this angle and the angle bisector of this angle here are perpendicular to each other. That's because if this angle here is theta, then that's theta as well, and which means that this angle here is 2 theta, implying that this one here is 180 minus 2 theta. So, and since we have half is 90 minus theta. And then 90 minus theta plus theta is equal to 90 degrees. So since angle IBIA is equal to 90 degrees, that means that BIA is an external angle bisector of angle ABC. And we also know something similar for CIA, and it's an angle bisector of angle ACB. External angle bisector, sorry. So IA is actually the intersection of the exterior angle bisectors. But you guys can search this up. It turns out that IA, the intersection of the external bisectors, is the excenter of ABC, meaning that a circle can be drawn tangent to the BC and the extensions of both sides, and it's centered at IA. Sorry, this is a bad circle. It couldn't fit on the screen. Here's a better one. So that means that IA, the x center of this triangle here, the AX center, lies on this red circle here. So, and we can combine these results into what is known as a famous Incenter-Excenter lemma. Excenter. Which states that B, C, I, and IA are all concyclic, and moreover, the center of the circle is at the midpoint of the arc here. Well, since IA is a diameter, this would also mean that IA lies on AI, which is also really interesting. So this is not the full statement. So the center of the red circle is the midpoint of arc BC not containing A. And then, moreover, IA lies on this circle. And this ends up being really powerful in a lot of Olympiad problems. So make sure to keep this in mind next time. And for some reason, this is also called fact 5 for some reason. people like to call it fact 5. So whenever you hear of fact 5 or the Incenter-Excenter lemma on the internet somewhere, or on YouTube, or on AOPS or something like that, then you know what to expect here. So thank you so much for watching. Please subscribe, and I hope you enjoyed.